Hello, 5th grade math students. Here is chapter 11.4, which is all about theoretical probability and experimental probability. Probability is just a really fancy way to say the chance that something will happen. Let's begin by exploring theoretical probability. On the spinner shown, there are 6 possible color outcomes. The probability, or the chance, of getting any one of the 6 outcomes is 1 in 6. Because the sections are of equal size, each outcome is equally likely. Another example for this is tossing a coin. When you flip a coin, you have an equally likely chance of getting heads or tails. 1 out of the 2 options. If you're hoping the coin is going to land on its head, we would call that the favorable outcome. And your chance of getting that favorable outcome, the head that you're hoping you'll get because that's what you called, the chance of getting that is 1 in 2, or 1/2. We call this the theoretical probability. You know that the coin lands either as a head or as a tail. You predict that the outcomes are equally likely. If each outcome is equally likely, the theoretical probability of an event is the number of favorable outcomes divided by the total number of possible outcomes. So for flipping a coin, your odds are always 1/2. The theoretical probability, going back to our spinner here, of getting the color you want, let's say purple, would be 1 in 6. If you wanted to get yellow, your probability would still be 1 in 6. If you wanted to get red, your theoretical probability would still be 1 in 6, because the number of favorable outcomes will always be 1, and the total number of possible outcomes is equal to 6. Try this one on your own. A bag has 3 yellow beads and 5 green beads. Please answer the questions below to help you calculate the theoretical probability of drawing a yellow or drawing a green. There is another question in this practice, so pause while you work and move on when you are ready. Now try this practice. Brad rolls a cube numbered 1 to 6 on its faces. He then flips a coin. First, draw a tree diagram of the possible outcomes. You're going to use this diagram to answer questions 6 through 9. Then, what is the theoretical probability of 6 getting a head and an odd number, 7 getting a tail and a 0, 8 getting a head and a number less than 5, or 9 getting a tail and a number that is more than 1 and less than 6. Remember, refer to the tree diagram to help you count the number of possibilities, and don't forget, if you're putting these in fraction form, to make sure you are reducing them to give answer in simplest form. Now that we understand theoretical probability, let's dive into experimental probability. Jack and Jill carry out an experiment. They each toss a coin 20 times and record the results on a table. In Jack's experiment, the probability of heads from his coin tosses is 0.6 because out of the 20 tosses, he got 12 heads. In Jill's experiment, the probability of getting heads from the coin tosses was 0.45 because she got 9 heads out of the 20 tosses. The probability of Jack getting tails was 8 out of 20, or 0.4. And the probability of Jill getting tails was 11 out of 20, or 0.55. In both experiments, the probability of either heads or tails is still close to 1/2, or 0.5. Usually in experiments, your results are going to be close to the theoretical probability. However, the probability you get from actually doing the experiment is called the experimental probability. The formula for experimental probability is the number of favorable outcomes in an actual experiment divided by or over the total number of trials. For example, in Jack's case, if heads was our favorable outcome, the probability of getting heads was 12 out of 20. The favorable outcome over the total number of trials. The sum of the probabilities of an event occurring and not occurring should be equal to 1. Please note that in Jack's case, the probability of getting heads was 0.6. The probability of getting tails was 0.4. That equals 1. For Jill, the probability of getting heads was 0.45. The probability of getting tails was 0.55. That equals 1. Let's try this practice problem that uses both experimental and theoretical probability. There are 6 green prizes and 14 red prizes in a bag. In an experiment, Jesse and Keith draw a prize from the bag 100 times. Each time they return the prize that they drew to the bag. Their outcomes are recorded on this table. Complete this table. If Jesse drew 18 green prizes and 80 true red prizes, calculate the probability that she drew a green prize and the probability that Jesse drew a red prize. Keith drew the green prize 25 times and the red prize 75 times. Please calculate the probability that Keith drew a green prize and then the probability that Keith drew a red prize. Remember, probability is calculated by the number of favorable outcomes that were actually drawn over the number of trials. Please press pause while you complete this. There is one final practice problem on the next screen. And let's finish up chapter 11.4 with this final practice problem. A box contains some black, green, and white beads. Rosa picks one bead at a time from the box, records its color, and returns the bead to the box. She picks the beads from the box 18 times and then displays her results on this bar graph. Which set of beads is more likely to be the beads in the bag? Set A or set B? Okay, how are you going to calculate this? Here's what I suggest. Use the data that Rosa actually collected on this chart to calculate the experimental probability of drawing black, green, or white. Then calculate the theoretical probability of drawing black, green, or white from set A and from set B. Then compare the experimental probabilities that you calculated from the chart to the theoretical probabilities that you calculated from the blue chart, and decide which set, A or B, is closest to the experimental probability you calculated from the graph. Give it a try. Don't worry if you get stuck. We will definitely work this example together tomorrow. We'll also play several math games that let us explore the difference between theoretical and experimental probabilities of an event. So I'll see you tomorrow for that fun. Until then, thanks for your great work on learning theoretical and experimental probability today.